Hello everyone, my name is Pejman Najafi from Hasso Plattner Institute, University Potsdam, Germany. Today I'll be presenting our paper titled as SIEMA, Bringing Advanced Analytics to Legacy Security Information and Event Management. With no further ado, let's get started with the presentation. Let's start with a bit of introduction to SIEM systems. So SIEM stands for Security Information and Event Management. These are the systems within the typical organizations or enterprises that are expected to hold all relevant security-related data. The data sent to such systems can vary from basic alerts from intrusion detection systems, antiviruses, to wide range of event logs from servers such as proxy servers, firewalls, DNS, to endpoint and workstations such as Windows event logs. It could also include some OSINT aspect and other type of open source intelligence, such as threat intelligence, vulnerabilities, and so on. Such systems are expected to have a holistic view of all IT-related landscape within the enterprise. So traditionally, the original purpose of these systems were to meet regulatory and compliance requirements, such as PCI and HIPAA. Over time, they have evolved to support other purposes, particularly due to one main reason. As we said, these systems are expected to be the central repository of all security relevant data. That includes event logs, all data collected from the landscape, from every device from the landscape. Therefore, a holistic view over these heterogeneous data sources. And we could hypothesize that if there exists a threat that somehow managed to bypass the traditional defense parameters, we expect to find its traces somewhere in these logs. That could be our last safety net, right, in catching any unknown threats. Therefore, over time, more purposes were added to the SIEM systems, from the regulatory and compliances and information event management to other requirements such as threat hunting, investigation, event correlation, enrichment, rule-based pattern matching, and signature-based threat detection. The last one is an important one, as we're going to get back to it, which is the problem. So there are a lot of SIEM systems right now, and it's perhaps one of the most important system and tool used within mature organizations today. However, there are problems with them. Particularly, there are architectural limitations. They lack distribution. They lack the capability to be a distributed and scalable system, respecting everything that we learned from big data architectures and distributed systems. They're not usually extensible. They cannot support new state-of-the-art tools, technologies, and ideas. They're not so open. They have their closed data sources, the data formats, and they lack integration with some other important tools, as we will find out soon. Therefore, the architectural limitation leads to lacking advanced analytical capabilities, which is quite important. Looking at signatures and just rules is not the same as advanced analytics. There is a need and incapability of doing complex data engineering and complex state-of-the-art data science, such as statistical machine learning or data mining approaches to the problem of threat detection. To just give you a bit of more, give you a bit more ideas of what do we mean here, you can think of back in the day OLTP and OLAP systems. There are different systems or different ideas for a different purpose. The same as MySQL and Apache Edge-based. There are different technologies designed for a different purpose. Same as Elastic and Apache Spark. For those of you who know these technologies, you get where I'm going with this. These are technologies designed for a different purpose and for different reasons. Therefore, searching is not the same as analytics. And that's basically the core problem that we're trying to highlight within today's SIEMs, calling them legacy SIEMs, and what could be perhaps an extension of them, and why is it important to get there. That is actually the main reason why in this paper we are proposing the idea of SIEMA, which is adding analytical capabilities to the traditional SIEMs. While it is beyond the scope of this presentation to get into the detail of our reference architectures proposed in this paper, due to the lack of time. I would like to just bring your attention to the building blocks in this figure, where we try to present the abstract view of the main components that we understand is important for a SIEM that would now have analytical capabilities. You should be able to add technologies to this abstract reference architectures in order to support your needs. We will see in a few more slides what do we mean by that. But before getting there, I would like to bring attention to storage and the processing modules of such reference architectures. Every module here is expected to be modular, literally, and scalable, and consists of perhaps multiple layers. So when there's a big blob of storage here, it actually doesn't mean like a single storage, where you can think of it as an abstraction for storages within the system. Storages where it could be an index store, it could be a hot storage for queuing mechanism, it could be object store, it could be NoSQL databases. You can think of different needs, but all needs to be able to communicate nicely together throughout this architecture. For more information about each of these modules and what we consider their purpose and their importance, please refer to the paper. We were lucky enough that during our time to develop two systems based on this reference architecture. One, we call it an in-house research workbench, as we created it within the institute ourselves, putting technologies, open source technologies, and fitting it towards that reference architecture that I just talked about. And we were lucky enough to also get a chance to work with a large international organization to bring some analytical capabilities close to their SIEM by utilizing technologies surrounding their landscape. So within our open source research workbench, we used technologies such as Apache Spark for the main processing. We used different storage systems such as Cassandra, HDFS, Kafka, and of course Elastic for the string search. We also used other tools such as Najafi, Logstash to be able to get hold of the ingestion and basic pre-processing, and with some, of course, visualizations such as Kibana, Zeppelin, and Najafi itself for the orchestration. There were some other also like privately built tools as well, and we represented with this custom icon. And within the real-world enterprise, we got hold of Databricks, Azure ADLS, Data Factory, and Logic Apps for the main aspects of this proposed architecture. So having the capabilities now provided by the architecture that enables analytical capabilities, as it would respect everything we learned in big data architectures, now we can enable new purposes and new possibilities. We can perhaps get to the idea of data-driven SOC. We can look into everything that we learned over the last few years in data science, in the research of like data mining, graph theories, machine learning, deep learning, artificial intelligence, every science that has been put into use in different domains. We can learn from them and apply it to cybersecurity, and perhaps truly look for user behavior analysis, something that is not so easy as you have to define signatures. You need to be able to do large-scale analysis. We can look into vulnerable users, insider threats, data exfiltration. We can look into anomaly detection, truly anomaly detection within such systems. We can try to find malicious entities. We can try to ingest, correlate, and build automated pipeline that build this different use cases on top of each other, therefore complex data engineering, and perhaps get to a point where we can actually look for unknown unknowns. So in our work, we attempted to highlight the importance of advanced analytics and the need for extending traditional SIEMs with the architectural capabilities to support big data analytics with a simple yet difficult use case, particularly beaconing detection. So beaconing is basically the periodic attempts of the malware trying to reach its command and control for receiving instructions from the adversary. It is important as it could be very much characteristics of any type of advanced malware. One could look into beaconing detection using data sources such as NetFlow, DNS, proxy, PCAP, basically any data source that might have some sort of network traces in them, even EDR, because some of the EDR would also record the network connections. And possibly you can create a rule that look for periodic connection attempts among same source and destination pair. However, it's not an easy challenge. It's not a simple rule that you can define in a SIEM system as a signature or as a search, because it is a big data problem. You need to look into every source and destination pair and calculate the time of the connection and differences of those times to be able to see how periodic it is. There's also the other problems, such as the beaconing might have some randomness or jitter to it. There are also the concept of false positives. There are a lot of benign applications that have beaconing behavior, such as updates or tools that needs to reach out to the service for a certain time. And there's also some other external factors. For instance, the endpoint going offline as it's the night they close the laptop, or the network connection not happening, therefore a new network connection needs to be made, and other external factors that could introduce more challenge. So not an easy task for a traditional SIEM. One has to think about this use case in order to build it. So if you try to get some sort of detection approach to this problem, we could highlight a very simple idea to approach this problem. So consider that these are data. We've got source, destination, the second column, and third, the time of the connection, source, destination, timestamp. So we could try to prepare the data in the format, so make sure these are timestamped, that's the destination correct, the source is correct. We can sort them basically also when we prepare them based on source, destination, and the timestamp. Then we can calculate the time deltas. So you see that there's 60 seconds difference of connections between each of them. So 1 minute. We need to clean these time deltas because you can see the first one is null because there was nothing behind. And there's this ones that basically try to simulate, let's say that the laptop was off or the network connection didn't happen, therefore immediately there was another connection. We can attempt to clean those using some sort of IQR or basically percentile analysis. So getting rid of nth percentile on top or the lower bounds and get the middle part. So looking at the percentile analysis. So we end up with such a table that you can see on the right. So we see the source, destination, timestamp, converted the unique timestamp, and the time delta. We can use the very, very simple idea of calculating the periodicity via average and standard deviation. So the lower the standard deviation, which implies perfect periodicity. So meaning that every 60 seconds, this source is connecting to this destination. And we can see that is 10 beacons, perfect. We can calculate some sort of reputation of every destination, which means that, for instance, beaconing x.com is observed only accessed by one source, so therefore let's give it 1. Given this information, we can derive some sort of scoring mechanism, so one can go crazy here or just do some very, very simple ideas to be able to rate how good every beaconing case is. We can look at some very basic stuff like such as how good the periodicity is, what's the destination reputation, so the lower the better, and what about the beaconing consistency. So all these formulas here will refer to the paper for the details, but all they would ensure is that how good it is between 0 to 1, 1 being the highest beaconing risk and 0 the lowest. And we get some sort of weighted average of them and alert on top of the highest scored beaconing cases. So with a very, very simple approach, you get the logic here. So we use the logic described in the previous slide to set up an experiment within our partner's environment. Particularly, we used 1 day of EDR logs, which would count towards 172 million events spanning on over 102 gigabytes of data on disk. We used the traditional SIEM systems and compare it to our extension of SIEMA implementation next to the SIEM. Due to the NDA requirements, we cannot reveal the setup of their SIEM system, nor the vendor used. However, we can acknowledge that perhaps this was one of the largest SIEM deployments in the world, as this organization is a large international organization with more than 90,000 employees. And the SIEM system is one of the highest rated SIEM vendors according to Gartner SIEM report. We compared that to our SIEMA extension, which was mostly on Databricks connection to ADLS. The Databricks counting with 5 standard workers, coming up to 640 gigabits of memory, 160 cores, and 1 terabyte. While it is important to ensure it is actually important that there are so many variables in play to make this comparison fair, such as the configuration of the systems, the underlying servers, their speed, the actual setup. So a lot of variables in hand. We hope that even though that there are so many unknowns here in this experiment, we still be able to highlight the importance of building advanced analytics within the core of the SIEM, and why traditional SIEMs would kind of fail as they lack these capabilities, as they are not designed for distributed analytics. So we used the same logic described in the previous slide for the beacon detection. We implemented on their legacy SIEM, and we implemented on our extension, hence Databricks. So one running on Spark, one running on the legacy SIEM. It took 45 minutes on the legacy SIEM to go over 89 million events before it's reaching its disk limits, hence for failing, whereas it took 26 seconds to go through all events. As I said, while it is true that the comparison may not be exactly fair, but you get the idea that we are going from 1 hour down to the seconds, particularly on a SIEM that is designed to support an international enterprise with more than 90,000 employees and support the whole SOC cyber defense department of that organization. So it is not a small SIEM deployment. It is perhaps one of the largest, and yet it was incapable of running this simple beaconing detection. You can imagine what happens as we grow towards more advanced use cases such as machine learning, data mining, graph mining, other difficult ideas. We also try to explore the scalability. So one thing with the SIEMA that we discuss in this paper is how important it is to be scalable, respect distributed systems, respect idea of MapReduce style thinking. So within our extension, we could see that as we increase the number of the workers, we can reduce the runtime. We also explored what happens if we run it over 5 days of data. While the traditional SIEM didn't work, it only took 126 seconds within our extension, proving that there is a need for such systems. To conclude this presentation, I wanted to highlight that traditional SIEMs are still very much needed. In fact, we need them for investigation, we need them for threat hunting, we need them for monitoring, something that they were originally designed for, the technologies within them designed for that purpose. However, at the same time with this work, we wanted to highlight that they lack some capabilities, particularly advanced analytical capabilities, something offered only by respecting big data architectures, distributed processing, distributed systems, distributed storage systems. And at the same time, the fact that rule-based threat hunting is no longer enough. We live in an era that we need data-driven approach to this problem, just like any other domain which have evolved using data science to solve their problems. It is sad that cybersecurity has failed to evolve. Perhaps this could be our only way to find unknown unknowns, and this is not supported by majority of today's SIEMs. We hope this can motivate people to design and look for next generation SIEMs, putting either new technologies from scratch together or putting other technologies next to each other, therefore supporting and closing the gap between a traditional SOC analyst and today's data scientist. Thank you very much.